Okay, so we're finishing up with the worksheet 2-7 day 1, and this is where we sort of stopped in class. So um, we'll pick up with problem number 4 from the beginning. And if you remember, I said that to think about the square root of x times y, if you're going to take its derivative, it's better to think about it as x to the 1/2 and y to the 1/2 as a product, so that you don't have to use the general power rule and then in the midst of that use the product rule on x times y. So if we give each of them their own exponent, then we can just use the product rule, and then in the midst of that we'll have to use the general power rule, but it's easier that way. So this is the product of two functions. We'll take the first function and leave it as it is, x to the 1/2. Take the derivative of y to the 1/2, which is 1/2 y to the negative 1/2 dy dx, because we need a chain rule when we're taking the derivative of y to a power. Plus, we leave y to the 1/2 alone, and we take the derivative of x to the 1/2 as 1/2 x to the negative 1/2. We don't have a dy dx because x is not a function of x is x. So you could make it dx dx if you wanted, but that would sort of be pointless. Then we are moving on. So we took the derivative of this product and we ended up with this long string of terms, and now we are going to take the derivative of 3x, which is 3, and the derivative of 9, which is 0. So now you have a choice in terms of how you want to deal with this algebraically. I prefer to get the dy dx by itself before I deal with negative exponents. So if I'm going to do that, then I see 1, 2, 3 terms on the left-hand side that are connected by addition, and only the first one has a dy dx attached to it. So I would like to send the other two terms to the right and think about this as x to the 1/2. I'll put the 1/2 that's in the middle at the beginning, y to the negative 1/2 dy dx. So I just changed the order a little bit on that term. And I'm going to stick the other one, again putting the 1/2 first and the x next and the y third. 1/2 x to the negative 1/2 y to the 1/2. And that will be negative on the other side, and so will the 3. So I end up with my term with the dy dx on the left and the other two terms on the right. Now's the time to divide. So I can divide the left-hand side by all of the factors that are in front of the dy dx. And then I'll divide the right-hand side by those same factors, and I will have dy dx. Now, it's dy dx in a pretty messy form, so I have to think about that, but I can simplify that at this point now. And the easiest way to simplify it, because of this -3, I can't start moving things up and down because the -3 connects this whole numerator together. But I could multiply everything by 2, and by everything I mean this piece, and this piece. I could multiply them all by 2. And if I did that, then I wouldn't have the 1/2s anymore. So that would be a good thing. So I'll multiply this by 2 and turn the negative 1/2 into a negative 1. I'll multiply the 3 by 2 and make it a 6, and I'll multiply this 1/2 by 2 and make it a positive 1. The other thing I have to deal with is this negative exponent on x up here. I can't physically take it down, again, because it's connected to the 3. But what I could do is multiply everything by x to the positive 1/2. And by everything, again, I mean all 3 pieces. Just like I multiplied everything by 2. I'll just put that in there also. So when I multiply x to the negative 1/2 times x to the positive 1/2, that'll be x to the 0, so it'll be gone. When I multiply here, I'm going to get an x to the 1/2. And then when I multiply here, x to the 1/2 times x to the 1/2, I'm going to get an x because I add the exponents and it's 1. And I'll do the same thing with the y, because y to the 1/2 is negative down here, and I don't want it to be. So I'm just going to multiply by y to the positive 1/2 and turn that into y to the 0. I'm going to have to multiply this by y to the 1/2. So I'll get a y to the 1/2 there, and then up here, y to the 1/2. I'll add the exponents and I'll get a y. So that's the fastest way to deal with those negative exponents that I didn't want and the 1/2 living inside a fraction that I didn't want. And to me, that's the best way to go. But there are other ways to approach it, and as long as we agree on our answer, you can go ahead and do it however you want. Next problem has a little star by it, number 5, because you want to think before you start. If you look at it and you just start taking a derivative, you would need the quotient rule. And that would not be the best way to approach it, because you're going to have the quotient rule, and in the midst of it, you're going to have a product rule, and you're going to have a big mess of algebra. So before you take the derivative, the best thing to do would be to cross multiply. And if you cross multiply, putting a 1 under here, then you're going to end up with xy minus y squared equals 6 times y minus x. You can write it like that. Or because we're going to have to take the derivative and move things around, it probably would be better to say 6y minus 6x and just keep all the terms separated by subtraction. So then I can start going left to right and taking my derivative of everything that I come in contact with, and I won't have to do the quotient rule. I do have to do the product rule here, so x left alone times the derivative of y dy dx plus y left alone times the derivative of x, which is 1, minus, move the 2 down, drop the degree on y to 1, times the derivative of y, which is dy dx. And I'm going to erase that 1 because I don't want you to think it's a y prime. And then on the other side equals 6y derivative is 6 dy dx. 6x derivative is 6. So left to right, I took all the derivatives, and now I have a problem because the dy dx's are on opposite sides. And that's what I'm trying to solve for. So my strategy here, again, is to focus on how many terms I have. The terms are separated by addition and subtraction. So I see all 5 of those there. I'd like the ones with the dy dx, which are this one, and that one, all on one side. Now, I want to check because I'm like, wow, 3 dy dx's, that's a lot. But there were 3 y's in the problem, and that's why I have 3 dy dx's. So I'm going to leave my x dy dx and my negative 2y dy dx where they are, and I'm going to move the 6 dy dx over, which makes it negative. And then I want to keep the negative 6 where it is on the right. I would like this y term that doesn't have a dy dx to go over with it. So I'm going to move it over to that side, and I can write negative 6 minus y over there. Now's the time to factor my dy dx out of the left. So I have x minus 2y minus 6. And on the right-hand side, I still have my negative 6 minus y. And once it's factored out, I can divide away. And I will be left with a final answer of dy dx equals negative 6 minus y over negative x minus 2y minus 6. And I know that nobody is tempted, but I'm just going to make the comment, this negative 6 cannot divide out that negative 6 because they're connected by subtraction, not multiplication. So we're just going to leave it like that. And then the final problem on this page is testing a little bit about what does it mean when you say dx dp, as opposed to what we normally would say is dp dx. Usually the dx is in the bottom because we're differentiating a function with respect to x. So the way this is written, dp dx would be easy to find because it says p equals. So if it says p equals, then dp dx can be found explicitly. And so that's sort of what you hope for, that they wanted me to find dp dx. But they don't. They want me to find dx dp. So now I got to think about how am I going to do that. There's two choices. One choice would be, okay, I want dx dp, so I'd like this thing to say x equals. And if it says x equals, then I can explicitly differentiate dx dp. So that's one choice. So I look at my problem and I say, oh, all right, well, I don't want to say p equals. I want to say x equals. So how did I fix that last time? Hopefully remember we switched on the diagonal and we said 0.03x plus 5 equals 4 over p. And then I can solve this for x. So I can subtract 5 from both sides, and then I can divide both sides by 0.03. So I'm going to get something that looks like this. So that's one way to deal with it, to make it say x equals. Now, of course, you really don't want to have a decimal inside your fraction, so we're going to have to fix that. 0.03 is 3 out of 100. So if I have a 3 out of 100 in the bottom, I can flip it over and it would be 400 over 3. And the p is in the denominator, so I'm going to call that p to the negative 1. And then here I'm going to flip it over and I'm going to make, this is 3 over 100, so if I flip it over it's 100 over 3 that I'm multiplying by 500 over 3. So that's a better way to write it rather than a decimal inside a fraction. But now that it's written x equals, it's easy to get dx dp, the derivative of x with respect to p. And that is simply going to be, since I'm doing it explicitly, I'm going to move the negative 1 down, drop the degree to negative 2, take the derivative of this, and it's 0. So it's negative 400 over 3p squared, dx dp. That's the derivative of x with respect to p. Now, what does that mean? That's another thing you need to understand. The derivative of x with respect to p, this is a demand function. And derivatives represent a rate of change. So in words, this is the rate of change in the number of units demanded as the price changes, or with respect to the price that I'm given. So this is an interesting thing to know. What is the rate of change? How fast is the demand for my product changing when I change the price? So if I drop the price, is it going to make a big difference in how many units are going to be demanded? If I raise the price, will it make a big difference? It's an important thing for people to know, the rate of change in the number of units demanded as the price changes, as opposed to dp dx, which really makes no sense in economics, because that would be the rate of change of the price when I change the number of units demanded. The denominator is what you're manipulating, in other words. So here I'd be manipulating demand, or the number of units that I can sell. And that doesn't make any sense. I can't manipulate the number of units that people are going to demand. The only way I can do it is by manipulating price. So If I change the price, then that will change how many units are demanded. So the one that makes most economic sense is dxdp, even though the demand function might be written P equals, which it is if I need to find the revenue function. That's not the best way to think about it if I want to find dxdp. So something to think about for the test. You want to definitely know the difference between those two concepts and how you can get one of them, the one that makes the most economic sense. So if you can solve for the variable that's in the numerator of the derivative you want to find, dxdp, that's what you want to do. And sometimes you can and sometimes you can't. If you can't, you're going to have to implicitly differentiate.